Okay, good afternoon, students. So welcome to the third Chemistry Olympiad training session. So this is our third training session already. So we are on set number 3. Today we will be doing covalent bonding and metallic bonding. So two different types of bonding, all right? So let's just do a very quick recap of covalent bonding. The covalent bonds are formed when valence electrons are shared. And this usually happens between two or more non-metal atoms. So the keyword here is sharing. We are sharing the valence electrons, and which types of elements form covalent bonds? The type of elements that form covalent bonds are non-metals. So take, for example, chlorine, fluorine, hydrogen, carbon. These are examples of non-metals which will share valence electrons with each other. Okay? So, in essence, covalent bonds will be the force of attraction between the nuclei, so between the nucleus of the two atoms, and the shared electrons. That's why the shared electrons remain where they are. So take, for example, I've drawn Cl2 for you. This is Cl2. This is the dot and cross diagram with the shared electrons in the center. Why do the shared electron pairs stay there? Well, they stay there because the shared electrons are attracted to the nuclei of the two chlorine atoms. The shared electrons are attracted by the chlorine on the left. They are also attracted to the nuclei of the chlorine on the right. Same with HF. All right. So this is just a quick recap of covalent bonding. Now, let's go deeper into how to draw dot and cross diagrams. Okay, I know this diagram looks quite complicated for you, but in essence, to draw a dot and cross diagram really isn't so difficult. The first thing you need to do is to get the chemical formula right. For example, carbon dioxide is CO2. If you know it's CO2, it means it has one carbon atom and two oxygen atoms, right? CO2, one carbon, two oxygen. Okay? One carbon, two oxygen. This means that carbon is in a lesser number because you only have one carbon atom. And because you only have one carbon atom, carbon needs to go into the center. Carbon is the center of the molecule. And that's why you see in the dot and cross diagram, I will put carbon in the center. Okay, so carbon goes to the center, oxygen goes to the sides. I know it's covalent bonding because these things, they are non-metals, so they must share valence electrons. Okay, so if I know it's sharing and covalent bonding, I will overlap the electron shells like what I have just done. Next, I will consider the atoms at the side. The atom at the side is oxygen. Oxygen, if I look in the periodic table, has 8 electrons. 2 first shell, 6 second shell. So oxygen has 6 valence electrons. If it has 6 valence electrons, it's not stable because the valence electron shell is not fully filled. To make it fully filled, it needs to have 2 more. Each oxygen needs 2 more electrons in order to achieve a fully filled outermost electron shell. Right? Because fully filled means 8 electrons. Currently, I only have 6. So it needs 2 more. If it needs 2 more, it has to share 2 electrons. So what does sharing 2 electrons look like? I share one with you, you share one with me, dot and cross. But I'm sharing 2, so it's dot cross, dot cross. Same with the other side. All right? Now, finally, you need to realize the purpose of sharing electrons is so that the outer electron shell is fully filled. Fully filled means 8 electrons. So currently, if you look at the oxygens, I have only drawn dot cross, dot cross. Dot cross is a total of 4 electrons, meaning there must be 4 more outside in the valence shell which are not shared. Why 4 more outside? Because I know a fully filled valence electron shell must have 8 electrons. Okay? So since I've drawn 4 which are shared already, I must have 4 more outside which are not shared. How about carbon though? The carbon in the center also needs 8 electrons. Does it already have 8? If you count, dot cross is 4, dot cross is also 4 on the right. So in total, carbon has 8 electrons, including the shared electrons, in its valence electron shell. Okay, so that's how we draw a dot and cross diagram. Okay, now we can go on to more examples. So take for example, how will we draw NCl3? Same principles. First step, you need to know that nitrogen, there's only one of it. Therefore, nitrogen goes to the center. So when drawing the molecule, the covalent molecule, N must be in the center, followed by Cl, Cl, Cl on the sides connected to N. Okay, so the Cl don't connect with Cl, the Cl connects with N. So the molecule has to look like this. Where nitrogen is in the center, chlorine goes to the sides. Next step, we consider chlorine. Because I know chlorine is at the side, I must try to make chlorine have a fully filled outermost shell first. Chlorine, if you go to the periodic table, has 17 electrons. So if chlorine has 17 electrons, it's arranged 2, 8, 7. It has 7 valence electrons. So each chlorine has 7 valence electrons, which again is not stable. It's not a fully filled valence electron shell. So it needs 1 more electron. So it shares 1. So chlorine will have to share 1 electron with nitrogen. Sharing 1 is just 1 dot, 1 cross, 1 dot, 1 cross. So each chlorine shares 1 electron. Okay? Can? So this is our second step. Consider the atom at the sides, which in this case is chlorine. Try to make sure that chlorine has a fully filled outermost electron shell. How do I do that? I must work out chlorine is 2, 8, 7. 7 valence electrons. It needs 1 more to make the outermost shell fully filled. Hence, it shares 1 electron. But that's not it. There's still one last step. You need to ensure that each atom has a fully filled outer shell. And how do I do that? I have to fill in the rest of the electrons. So chlorine, if it's fully filled, must have 8 electrons. I've only drawn 1 dot, 1 cross, meaning outside I need to draw 6 more. So that in total, I have 8 electrons in the outer shell for each chlorine. Okay. So I have to draw 6 more electrons for each chlorine in its valence shell. But is that the only thing? We also need to consider nitrogen, which is at the center. I have 2, 4, 6 shared electrons in total. This means that nitrogen still needs 2 more on the outside of it in its valence shell. Okay. Now this is a dot and cross diagram. Yeah. As you can imagine, the dot and cross diagram requires a few steps to draw. It takes some time to draw, but you need to go through this thinking process. Now, typically, right, in textbooks, we don't usually represent molecules with dot and cross because it's too messy, especially if the molecule is too big. So we will use what we call the Lewis diagram. So this is the Lewis structure. The Lewis structure shows bonds, covalent bonds as lines. So each covalent bond, one line is one covalent bond. And each covalent bond has 2 electrons. Okay, so that's called a Lewis structure. Dot and cross is what's on the right-hand side. Okay, they are the same molecule, it's just different ways to draw it, different ways to represent it. Okay, Ken? Now, just based on this alone, you can predict many things already. Immediately, something that comes to your mind is the electron on N, which is not shared. This is called a lone pair. As the name suggests, it's a lonely pair of electrons that is not shared. Whenever you have a lone pair, it means that the molecule is quite reactive. It is able to donate these lone pairs to other molecules, which may require electrons. Okay? So just bear this in mind. If you go on to do more chemistry at A level, for example, you will spend most of your time drawing molecules like these, talking about lone pairs. Okay, NCl3 is quite reactive. NCl3, if you were to touch it, it will explode. It's a contact explosive. And the reason why it's so reactive is very largely due to the lone pair on nitrogen. Okay, so this is a brief recap for my Sec 4s. How do we draw a dot and cross diagram? The 3 steps involved. For the 3 contribute students, I believe you also just did this topic in class. So hopefully it serves as a good recap for you as well. Okay, so this is how we draw a dot and cross diagram for a covalent molecule. Moving on. I know I've asked you to draw dot and cross diagrams for the following molecules, show outer electrons only. I would like you to try this yourself later on. I will post the answers up on OneNote, which I will also remind you when I have posted it onto OneNote. So do it yourself as part of enrichment. Later on, check your answers with the OneNote. If you still haven't been able to access the OneNote, you can do so by logging into Microsoft Teams on your iPads. So go to Teams on your iPad. You should be able to see that you have been added into the Chemistry Olympiad 2023 notebook. So go to Teams, find Chemistry Olympiad 2023, then you should be able to access the class notebook from there. If you are still having problems with Teams and OneNote, please find me in person when you get back to school. Okay, so this is really your homework. Next, let's move on to more advanced topics. So covalent bonding is the sharing of valence electrons. We usually assume and imagine that these shared electrons will be in the center, midway between the 2 atoms. But is that really true? Do the shared electrons really appear midway? Well, the answer is no, it doesn't. All right. In some cases, it doesn't appear midway. So what are those cases? Elements in a covalent bond may not share electrons equally. This is when you have some elements being more electronegative. So what is the meaning of electronegative? Electronegative means the elements have a higher tendency to attract shared electrons in a covalent bond. More electronegative attract shared electrons to themselves. It's like playing tug of war. It's not right in the center. There's one party that is stronger. In this case, more electronegative. That's why it's able to pull, attract the shared electrons closer to themselves. So electronegativity has values. We are able to experimentally determine these values. And it's given a numerical scale from 0 to 4. All right? 4 being the most electronegative. So if you look at the selection of elements that I have here, quite clearly, fluorine is the most electronegative. What this means is that if fluorine were to form covalent bonds, it will have the highest tendency to attract the shared electrons to itself. All right? And for my Sec 4 students, you have learned redox. This is the reason why the oxidation state of fluorine F is always -1 in a compound. There will not be any compound where the oxidation state of fluorine is positive. Fluorine will never be positive. It will only be negative because fluorine is the most electronegative element in the whole periodic table. All right. On the other hand, you can see quite clearly on the other extreme, the ones with the lowest is usually the alkali metals. What are alkali metals? They are in group 1. Okay, alkali metals have the lowest electronegativity. Okay, I've written one like this. This is because in the new periodic table that SJChos are using, the 1 is a numeral like this. For my SJC4 students, the 1 should be written like an I. That's the older periodic table. Okay. So generally speaking, alkali metals have the lowest electronegativity, like sodium. Sodium is in group 1, very, very low electronegativity. And this is also the reason why group 1 metals, the oxidation state will only be +1 in the compound. It's not going to be any negative number. Okay. Now, the key thing is, once you know the electronegative values, you can work out where the shared electrons will be. Will it be closer to this element or that element? All right. Now let's go straight to the example below, which is HCl. Now HCl is called hydrogen chloride. If it's dissolved in water, it's called hydrochloric acid. So there's a common acid that you find in lab. Now, HCl is obviously a covalent molecule. Hydrogen is non-metal, chlorine also non-metal. Okay. Now, hydrogen and chlorine share electrons with each other, but are the shared electrons midway, equal distance from each atom? The answer is no, because if you look at the table of electronegativity values, chlorine is more electronegative. Chlorine's electronegativity, if I'm not wrong, is 3.0. Yeah, 3.0. Hydrogen is 2.1. Meaning chlorine is more electronegative than hydrogen. So chlorine, being more electronegativity, will attract the shared electrons towards itself. So the shared electrons are actually closer to chlorine. It's still being shared, but the sharing now is unequal because the shared electrons are closer to chlorine, further from hydrogen. Okay? Now, as a result of this, the electrons are closer to chlorine, electrons are negatively charged. You learned that in atomic structure. Electrons are negatively charged. If the electrons are closer to chlorine, there's a partial negative charge. This is called delta minus. Okay, you write it like that. It's like an 8 that's not complete. Delta minus. So the delta minus n lies on chlorine because that's where the partial negative charge is. The delta minus is always the more electronegative element. More electronegative. Okay? On the other hand, the less electronegative, in this case, hydrogen, will have a delta plus on it. Okay? Hydrogen, delta plus. Now, these are partial charges. It's not a full positive charge. Why not a full charge? Because the electrons are still being shared. They have not lost electrons or gained electrons to form ions yet. Okay? Remember ions, Na+, Cl-, Mg2+. These ions are formed when things lose or gain valence electrons. Over here, it hasn't lost or gained electrons yet. We are just saying that the shared covalent electrons, they are closer to the chlorine. That's it. Okay? Now, generally speaking, a covalent bond is polar. This covalent bond is polar because got charges, partial charges. The moment you have partial charges is considered polar. And this usually happens if the difference in electronegativity is 0.5 or more. Difference means what? I take the more electronegative elements minus the less electronegative element. In this case, chlorine. Chlorine is 3.0. Hydrogen, 2.1. So 3.0 minus 2.1 equals 0.9. So the difference in electronegativity in HCl is 0.9. Therefore, it's polar. All right. And for my Sec 4 students, hopefully you realize why HCl is acidic now. If you were to dissolve HCl in water, it's quite obvious that it will form H plus ions. Because even as a covalent molecule, HCl is already polar. There's a delta plus on H already. So once you put into water, it will form H plus. Okay? So just now, I had a few questions about water. H2O is water, right? Is water polar? Well, let's look. Oxygen, 3.5. Hydrogen, 2.1. If you were to now calculate the difference in electronegativity, it's obvious. 3.5 minus 2.1, that's 1.4. The difference in electronegativity is 1.4. Definitely water is polar. Okay? And that's why water can dissolve ionic compounds. Ionic compounds dissolve in water because water has partial positive charges and partial negative charges. So take for example, if I were to dissolve sodium chloride in water. Sodium chloride is made of Na plus, Cl minus. Na plus ion is attracted to the oxygen. Cl minus ion is attracted to the hydrogen. These forces that I will highlight, these forces that I've highlighted in blue, these are called ion dipole interactions. They are the interactions between ions like Na plus, Cl minus, with the dipole. Dipole means covalent, polar covalent bond. Okay, so you can take this term down. Later, you can also search it up, okay, to see other examples of ion dipole interactions. And because water is polar, it is able to form such ion dipole interactions with ionic compounds. That's why ionic compounds can dissolve in water. On the other hand, ionic compounds don't dissolve in organic solvents like oil because oil is not polar. Okay. So this is more advanced. You will typically learn this at A level, but it's good to know for Chemistry Olympiad. All right. So at this juncture, as we finish electronegativity and polar covalent bonds, I hope you'll take a look at it. Think through your head. This is really about unequal sharing of electrons because the elements have a different tendency to attract the shared electrons. Okay. Now, let's do question 3 together though, okay? Deduce where the partial positive and partial negative charges would lie. So there are basically 4 examples here. Can I please give you about 5 minutes? Okay, let's work on these 4 examples. I want you to label where the delta plus and delta minus will be. Which atom is it on? Is it on H? Is it on C? Is it on O? All right, so let's label that. All right, so let's start. And please remember, polar if the difference in electronegativity is 0.5 or more. Okay? So think first, carbon and hydrogen. Is the difference between carbon and hydrogen 0.5 or more? All right. So you can make use of the values given to you on the previous page to work it out. So I give you 4 minutes to work it out, right? 2 more minutes to work it out. I've had the chance to think through it at least. Okay, let me just quickly go through the electronegativity values. Hydrogen is 2.1, carbon is 2.5, oxygen is 3.5, chlorine is 3.0, right? So these are values that you can get from the electronegativity scale. Okay, do I memorize these values? I do for some of the common ones like these, but having said that, you can easily search it up even as a chemist, so there's no need to memorize the exact value. Having said that, it's quite obvious from the values I've listed, the carbon-hydrogen bond, CH bond, is not polar because CH 2.5, 2.1, 2.5 minus 2.1 is 0.4. So a CH bond is not considered a polar bond. However, it's obvious this bond, the CO bond, definitely is polar. Okay, and it's quite easy to tell where the negative is going to be. Oxygen. Oxygen is more electronegative than carbon. So carbon is positive. Another bond that's polar is, of course, OH. Definitely polar, as we saw with water just now. So again, oxygen is negative because it's more electronegative. Hydrogen is where the delta plus is. Okay, so you can see quite clearly, this is how the partial positive and negative charges are distributed in the molecule of ethanol. Ethanol is the alcohol that is used in hand sanitizers. That's what you use throughout the past few years as hand sanitizers. Ethanol is polar because it contains the CO and the OH bond. All right. Next, propanone. Propanone, again, you can discount the CH bonds. The CH bonds are not polar. The polar one must be this one, the CO double bond. All right. Again, oxygen, carbon. Oxygen being delta minus, carbon being delta plus. All right. Propanone has a more common name that you might have seen more often. It's called acetone. ACETONE, acetone. All right, propanone or acetone is commonly used in nail polish remover. It's also used in thinners to actually remove paint. Okay, ethanoic acid is the next one. Ethanoic acid, again, CH not polar, but CO definitely polar. OH also polar. So I'm sure you can easily tell the oxygens definitely is where the minus is. The carbon is where the plus partial positive will be. Okay. Now, ethanoic acid, again, is polar. Ethanoic acid has a common name, which is vinegar. The main component of the vinegar that we eat is ethanoic acid. All right. Finally, the last one, chloroform, trichloromethane. So again, CH is not polar, but CCl is polar. CCl is polar because chlorine 3.0, carbon 2.5. 3.0 minus 2.5, that is 0.5. Okay. Chlorine is more electronegative than carbon. Okay, so that's how the partial positive and negative will be in a molecule of chloroform. Okay, so that's how it works. So hopefully you have gained some new insights. You have learned that, oh, maybe the covalent bonds doesn't involve equal sharing all the time. It depends on the electronegativity of the element. All right, Ken. So let's move on. Okay, just give me a minute. Okay, moving on. What affects the strength of covalent bonds? Now, this one I will go through quite quickly. All right. There are three main factors affecting the strength of covalent bonds. The first factor is bond order. What bond order means is whether the bond is a single, double, or triple bond. So you have seen some bonds are double bonds, some bonds are triple bonds. All right. It depends on the molecule. Double bonds have two lines. That means they have two pairs of shared electrons. Triple bonds have three pairs of shared electrons. Double bonds are generally stronger than single bonds. Triple bonds are generally stronger than double bonds, of course. Because the higher the bond order, the more shared electrons you have. Okay? However, you would quite clearly notice a double bond is not twice as strong as a single bond. How do I know this? Because there are values to back this up. Now, this table shows you bond energy on top. Right? You can clearly see the double bond is 610 kilojoules per mole. What this means is that you need to take in 610 kilojoules of energy to break the double bond. But 610 is less than twice of 350. The single bond only requires 350 kilojoules to break. The double bond 610. 610 is not 2 times of 350, right? It's less than that. So you can tell that a double bond is not twice as strong as a single bond. Okay, and now this is because of orbitals. Remember the last lesson we went through orbitals? All right. To form the double bond, the two bonds that are formed in a double bond uses different orbitals. Some orbitals don't overlap as well. So you can see the second bond in a double bond involves what we call side-on overlap. It doesn't overlap head-on, it overlaps sideways. And because it overlaps sideways, the overlap is not so effective. Therefore, the bond form is not so strong. Okay? Okay. Moving on, next, effectiveness of orbital overlap. Okay? Small orbitals have smaller atoms have smaller orbitals. That's the first thing. How do I know an atom is smaller? Look at the period. When you go to periodic table, you can find the period, right, from left to right. Okay, period 1 is smaller than period 2. Period 2 is smaller than period 3, and so on. All right. So the smaller atoms have smaller orbitals, and smaller orbitals overlap more effectively, and so the covalent bond is stronger. How do I know it's more effective? It's because as a percentage of the total orbital area, the overlap for a smaller orbital is higher. It's a higher percentage of overlap. When the orbitals overlap, it's a higher percentage because the orbital is smaller. If the orbital is very big, the overlap area is a very small percentage. So it's not so effective. All right. Finally, we just talked about difference in electronegativity, right? Polar covalent bonds are stronger. The more polar a bond, the stronger the bond. All right. So the greater the difference in electronegativity, the stronger the bond. Okay. So hopefully you learned by now, all these are covalent bonding and the factors that affect the strength of covalent bonding. Now, to be really honest, this is a topic that's quite advanced, but I think it's good for us to start thinking about it. So that at least we know that not all covalent bonds are equally strong. The strength of a covalent bonding depends on a few factors, including whether it's single, double, triple bond, including whether the atoms involved in covalent bonding are small atoms or big atoms. And also today we learned electronegativity. If the bond is polar, then it's a stronger bond. Okay. Now moving on, is one of those questions, okay, that come from the chemistry Olympiad. So this is electronegativity. It's one of the sample questions, right? So they want you to arrange the following in order of increasing ionic character. Increasing means from lowest ionic character to highest, most ionic. Oh, I thought we were talking about covalent bonding. Why now ionic? Remember, ionic bonding is opposite of covalent bonding, right? If it's the most ionic, that means the difference in electronegativity is the largest. If the difference in electronegativity is the largest, really one super electronegative, one not electronegative, then it's very, very ionic. Okay? Can? So based on this, we now need to order the following. So you can look CSBr, LABr3, the values of electronegativity are all given. So let's write it out. CSBr. CS, cesium, 0.7. Bromine, 2.8. The difference is 2.1. 2.8 minus 0.7 equals 2.1. LABr3, this is lanthanum bromide. Lanthanum, 1.0, bromine, 2.8. 2.8 minus 1, 1.8. So what can you say? Which one is more ionic? Cesium bromide or lanthanum bromide? The one that's more ionic must have the bigger difference. The bigger difference is cesium bromide. Therefore, cesium bromide is more ionic in character. So we can go on, PBr3, phosphorus tribromide, P is 2.1, 2.8, so again, 0.7, 2.8 minus 2.1. Okay, finally, MgBr2, magnesium bromide. Mg is 1.2, bromine 2.8, 2.8 minus 1.2, 1.6. So based on this quite clearly, if we go for the most ionic cesium bromide, we need to end with cesium bromide. It's the most ionic because the difference is the highest. Then it will be lanthanum bromide. Then it will be magnesium bromide. And finally, PBr3. So this is the order. Least ionic, most ionic. So based on this, the answer will be A. Okay? Okay. So this is a sample question from the Singapore Junior Chemistry Olympiad. Okay. Okay, moving on. Now, for covalent bonding can form two structures. Firstly, it's called simple molecular structure. Simple molecular structure means it's made out of small molecules. And these small molecules are held together by weak intermolecular forces of attraction. So for example, CO2, H2O, these are small molecules. And in between the CO2 molecules, we have weak intermolecular forces of attraction. And therefore, it can be easily overcome with a low amount of energy. And that's why things with a simple molecular structure have low melting and boiling points. They are volatile, meaning they tend to vaporize, form a gas easily. Okay? Can? Next, things with simple molecular structures do not conduct electricity because there are no mobile ions, no mobile electrons. Finally, Most covalent compounds with a simple molecular structure, they are insoluble in water, but they dissolve in organic solvents like oil. Okay, so as I was mentioning, simple molecular structure look like this. Okay, CO2 has a simple molecular structure. There are weak intermolecular forces of attraction between the molecules. And it's these forces that are overcome when melting and boiling. Okay. Now, on the other hand, some other substances which have covalent bonding, they adopt a wholly different structure. And this structure is called giant molecular lattice. So examples of covalent substances that have a giant molecular lattice: diamond, graphite, sand. Diamond, graphite, silicon dioxide, or sand. All right. Now, diamond and graphite are interesting because diamond and graphite, they are both the same elements. Actually, they are carbon. Okay, they are allotropes of carbon. What does allotrope mean? Allotrope means it is the same element, but they have different structures. The connections between carbon atoms in diamond is not the same as graphite. So let's look deeper. In diamond, each carbon atom is covalently bonded to 4 other carbon atoms. On the other hand, in graphite, each carbon atom is only covalently bonded to 3 other carbon atoms. All right. This has important impacts later. Okay. Next, because it's bonded differently to a different number of carbon, therefore, in diamond, you have a tetrahedral structure. Tetrahedral is this shape. This shape is called tetrahedral shape. All right. Some people may call it a triangular pyramid. Okay, tetrahedral. All right. Graphite, on the other hand, has a hexagonal shape. It's made out of hexagon layers. And in each layer, you have carbon, 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 carbon. Okay. So it's all these red dots that I'm marking out, they are carbon atoms. All right. Now, so what you realize is that substances with a giant molecular lattice, they don't have intermolecular forces, all right? Generally, except graphite, right? So, in order to melt diamond, graphite, silicon dioxide, we need to overcome the strong covalent bonds, even for graphite. Because for graphite, to separate the atoms, to melt it down, I need to separate the carbon atoms. To separate the carbon atoms, I must overcome the strong covalent bonds between the carbon. And a lot of energy is needed to do this. Okay? Now, on the other hand, you need to know, okay, you can see graphite is beginning to look a bit strange. Graphite conducts electricity. Now, graphite is actually found in your pencil lead. Your pencil lead is made of graphite. And if you connect it to a battery and a light bulb, the light bulb will light up. Tells you that graphite is a good conductor of electricity. Why? This is linked back to the fact that each carbon atom in graphite is only bonded to 3 other carbon atoms. Not 4, 3. Carbon has 4 valence electrons. It only bonded to 3 atoms. This means there's 1 valence electron that is not used in bonding. Whenever you have a valence electron that's not used in bonding and it's like a giant molecular lattice, the electron can be delocalized. This 1 valence electron per atom can move freely. It is not fixed to any atom. It's delocalized. Delocalized means not fixed. The electron can move freely. And when the delocalized electrons can move freely, it will conduct electricity. Okay? Finally, graphite, unlike diamond, is very soft. And that's because there are weak intermolecular forces of attraction between the layers of carbon, which can slide over one another easily when a force is applied. Okay? Now, for the Sec 3 students, you will learn this quite soon. Okay, as one or 2 lessons. Okay, for my Sec 4 students, hopefully this is a useful recap for you from last year when we did diamond and graphite. Okay, so with this, actually, I believe, okay, so there are more structures that I've printed for you. So it's not just diamond and graphite, okay, there are other substances that also have a giant molecular lattice. I have broadly divided this as diamond-like or graphite-like. So take, for example, diamond-like structures are like silicon carbide. cubic boron nitride. Okay, so these structures you can see, the way the atoms are connected looks more similar to diamond, whereas graphite-related structures, these are more similar to graphite, meaning they will have properties that are more similar to graphite. Okay. So this is a question about carbon nanotubes coming up. Carbon nanotubes are cylindrical molecules whose structure consists of a single layer of carbon atoms. All right. Now, which of the following statements are true? Is it similar to diamond? So refer to my notes, carbon nanotubes, they are more similar to graphite. So this is wrong. It should be more similar to graphite. Okay. Next, CNT are polymers. Now, this one you haven't learned, but it's wrong. CNT are not polymers. Polymers means you start with small molecules and join them together to form a big molecule. But you didn't start with small molecules, you started with atoms. It's made of atoms, so it's not a polymer, all right? Next, CNTs are stable at room temperature. Okay, this sounds reasonable, sounds plausible, right? But let's look at the last one. Conduction of electric current via CNTs is a chemical reaction. No, right? It's just like graphite. In graphite, you don't change the graphite chemically when you conduct electricity. It is just the delocalized electrons moving along the layers. There is no chemical change. Your pencil lead, when it conducts electricity, it doesn't change. It still remains like graphite. So similarly, carbon nanotubes don't change chemically. It's still carbon nanotubes before it conducts and after it conducts electricity. So the answer is C. CNTs are stable at room temperature. In fact, CNTs, carbon nanotubes, are widely used today. All right, they are widely used in a variety of electrical devices because they conduct electricity, especially for electrical devices that are very small. If you want to make a very small yet very efficient, very light electrical device, you would use a carbon nanotube. Carbon nanotubes are light, they are small, they have very, very high conductivity. So definitely they are stable at room temperature. And you can predict this because graphite is also stable at room temperature, right? So given that carbon nanotubes are similar to graphite, they should also be stable. All right, moving on. So today we are doing good on time. Let's move from covalent bonding to the last type of bonding, which is metallic bonding. Now, as the name suggests, metallic bonding is the bonding found in metals. Metals like copper, iron, magnesium, calcium, sodium, potassium, all metals will have this form of bonding, metallic bonding. So what is metallic bonding? So metallic bonding involves the valence electrons in the metal atoms, which are delocalized. So these are delocalized electrons in a metal surrounded by, of course, the metal cations. So what is the force of attraction? The force of attraction, of course, is between the cations, which are positively charged, and the delocalized electrons, which are negatively charged. So we say that the metallic bond is the strong electrostatic force of attraction between positive metal ions and the sea of delocalized electrons. Okay. Can? So immediately you realize, oh my God, we are back to the strong electrostatic forces of attraction. This means that metals, in order to melt them or boil them, you will need a lot of energy in order to overcome these strong electrostatic forces of attraction. As a result of that, you can imagine metals have a high melting point, which is true. That's what you learned in Sec 1, right? Metals have a high melting point. Now, but today, let's talk about what affects the strength of metallic bonds. Metallic bonds involve delocalized electrons. So clearly, if there are more delocalized electrons per atom, then it will have stronger metallic bonds. So take, for example, group 1. Group 1 only has one delocalized electron per atom. because only the valence electron is delocalized. Group 2, 2 delocalized electrons. Okay. So for the sec 3, sorry, your 2 is written like normal 2. For my sec 4 is II. So group 2, 2 delocalized electrons per atom, which means that group 2 metals will have stronger metallic bonds because there are more delocalized electrons. Okay? As a result of that, magnesium is from group 2. Magnesium has stronger metallic bonds than sodium from group 1. Therefore, magnesium has a higher melting point. Okay? Next, the metallic bond strength also depends on the metal cation, specifically the charge density of the ion. Charge density is charge over radius. If it's more highly charged and smaller, it will have a stronger electrostatic force of attraction. This is a concept that you must know. More charge, smaller, stronger electrostatic force. All right. So for example, if you have aluminium is group 3 or group 13. All right. Al3 plus has a higher charge. Definitely, it will have a stronger force of attraction. And that's why aluminium metal has a higher melting point than other metals like potassium, because potassium is K+. All right. So we can easily generalize the melting points of metals increase from group 1 all the way to group 3 or group 13. Okay. And I think that brings us to the end of today's training. All right, so you can see it's quite fast paced, but hopefully this serves as a good recap for you. The main learning point from today, hopefully, for all of you here, is the factors that affect the strength of covalent bonds, the factors that affect the strength of metallic bonds. So the next session, I will let you know what's the topic. We might do a bit of tweaks and adjustments to the schedule, but the next session will be next Wednesday at 5 p.m. All right. Same time, same Zoom link. So I shall see you next Wednesday. If you have any questions, please feel free to stay back in the Zoom room to ask me. Okay, I'll stop the recording now.